Hello all, good evening. We will start the session after 3 minutes. Let others also join. You wait for others to join. I'm audible, right?
Yeah, sir, you are audible.
Okay, thanks. Okay. So, hello, good evening all. Hope you all are fine. So, in the last session, not in the last session, I mean in the last open session, not in the live coding one, I asked all of you one question and told to think about it. Also, I accepted that it's quite readily available on the web, but still you should try to think about it. And that was the merge sort algorithm, but done in an in-place manner, right? So that we asked. So can someone tell, I mean, did any one of you think about it, how to do that? Any ideas? So, acha, let me ask this. What is the disadvantage of merge sort? So in week 2, we have learned the basic types of sorting and searching, right? We learned about binary search and all. In sorting, we learned about merge sort and selection sort, insertion sort. So we saw that merge sort was giving us order of n log n time, and that was the kind of the best case, worst case, and also the average case. Now my question is, what is the disadvantage of merge sort? Can you tell me, is there any disadvantage or is it the best algorithm for
So
sorting?
it doesn't sort in place.
Sorry, can you repeat?
It doesn't sort in place. You have to take it in an extra array and then sort them back together.
Correct, right?
With
Yeah.
Yes.
Yeah. So you have to take a temporary memory location and then you have to basically compare, when you are comparing two subparts of the array and considering these two subparts are sorted, you do the merge algorithm. Maybe at worst case it would take m plus n minus 1 comparisons, and that you have to place it in a temporary array and again copy that back into the primary array before returning that. So that's how merge sort works. So you need a temporary memory location to do merge sort. Other than that, there is also one more subtle disadvantage, but that's not a disadvantage when you are doing it on a small set of data, but that's certainly a disadvantage when you are doing it on a large set of data. But again, that I would talk about, that we would talk about, but let's come to that later. But before going to that, let's address this. So if I tell you you can do in-place merge sort, then I mean the only kind of disadvantage is getting solved, right? If we tell you that you can do a merge sort without taking an extra temporary memory location. So this was also the question I asked in the last open session. And I think I gave you hints that it has to do with using some mathematical tool. That's it, simple mathematics. The algorithm remains as it is. What you have to do is while modifying the value in the array, you have to just play a trick. And that has to do with some the percent operator. I mean, that is the remainder operator, modulus operator, multiplication, division, simple. So can someone tell? Did any one of you think about it?
Sir, I was not there for the last session, so I don't know what exactly you're talking about. If you can give the query again, maybe I can make an attempt.
Okay, surely. But so anyone else wants to say, except Vinod was speaking, right?
Yes, sir.
Okay, good. So except Vinod, anyone else who were there in the last open session? No one? Yeah, so I would briefly define the problem. I thought that today we would discuss the solution, but since none of you are telling, so I would just state the problem, and then maybe in the next session, hopefully one of you can tell it. Just a second. Okay, so what you all can see on my screen currently?
Blank screen.
Okay. The white screen, right?
Yeah.
Okay, fine. Yeah, so problem says you, the problem that I asked was, so merge sort's disadvantages, one of the disadvantages primarily the extra space that it takes. The question was, you have to think about a way out to not use that extra space while doing the merge algorithm. So obviously the merge sort, I mean, if you do the merge sort, right, how can we divide it? There would be a merge algorithm. I'm not going into the syntax, fine. So this is the merge algorithm. And then we would have the merge sort, let's call it merge sort algorithm. Fine. And this is basically a recursive call. So let's take, this is the body of the merge sort algorithm, right? Here you would write if that beginning to less than condition, right? If beginning is less than equal to end, what you do is you would calculate mid equal to beginning plus end by 2, fine. And then basically you would do the merge, right? Call the merge algorithm. You would call merge sort from, let's say this is the list or array, whatever you are working on. And then you send the starting index, the start value, which is beginning. Then you go till mid, and that's it. And Again, you go for merge sort recursive call. Again, pass the list or array, and now this time from mid to your last or end, right? End. And finally, you merge with the beginning, mid, and end. So what is the idea over here? The idea is these two calls, right, would break down your list one by one up to the bottom layer. That would be up to the single element that I have discussed in the previous open session, right? How the merge sort works. So when it breaks it down up to the single element level, after that this recursive this function call would happen, and it is assuming that the array part which is pointed out which is demarcated from beginning to mid and mid to end, that is sorted. So what I mean is, this is merge algorithm, right? So if this is my array and this is mid, so this part is sorted, and again this part is also sorted. This is pointed by end, this is my mid, and this is the beginning. Correct. Now the work of merge algorithm is simply combine these two sorted parts of the array into a final sorted array. That is, the whole thing would be sorted, right? That is the idea. And for that, merge algorithm takes order of exactly, if you say n plus n minus 1 in worst case comparison, so that's order of n comparison, right? But only thing is, it takes an extra memory space, because when you compare elements between these two, right, you compare, let's say, this element with this element, and then you place the smaller one into a separate memory location somewhere here, right? And accordingly you finally fill this whole temporary memory location with the sorted sequence and then copy it back. That's it. Now I don't want to use this extra memory location. Then how to do that? That is, I would have to modify the contents of this array only, right? I would have to modify the content of the array that I am operating on to do the comparison only, right? But again, if I need, I can get back the same elements which I have modified. So basically the idea is, this is my array, the same array on which I'm working, right? Let's say this is my middle, and these are the two elements that I'm comparing currently. Fine. Let's say between these two elements, this one is smaller. Okay, I would modify this value, right? I would swap, let's say, okay, let's say this one is smaller, not that one. Fine. Let's say this one is smaller. So if this is smaller, then it should come in the front, right? It should come over here. Correct. So I place this over here, but in such a way that if I again need the value, I can get it back. So basically you modify the same array in a way, in an intelligent way, that you can get back the value again if you need it for further comparison. Now I gave you a hint. The way to do that is, you have to, while you are writing now, so let's say in the merge algorithm, when you do if, let's say I'm denoting it by AI, right? AI is lesser than, right? Then we would copy. If AI is lesser than aj, and let's say I is starting from here and j is starting from here, then what we do, we place this ith element into a temporary memory, right? We would not do that. We would somehow edit the AI only. AI equal to something. Fine. Now this something should be planned in a way that if you require this value AI again, even after modifying, you can do a simple operation and get back the previous AI. And the hint was, the way to do that is, you have to put over here, right, some mathematical operation on AI, some function on AI itself, right, which would be constituting symbols, multiplication or division or the modulus operation. And one more hint, you may need the minimum element in the array list or the maximum element in the list. or let's state it this way, lesser than the minimum or greater than the maximum element in the list you would need. So basically this function would be a combination of one or more of these symbols and the lesser than the minimum value or greater than the maximum value of the list. Fine. It's a little bit difficult to think about, and I am again saying it's readily available on the web, so don't go over there. Please think it on your own terms. Fine. But at last, if you don't get it, since this is the second time I'm discussing this, you can go and check it out on the web as well. But try to understand the logic behind it. Huh? Just don't see it for the sake of it. Try to understand the logic behind it. Fine.
Sir, in this
So
problem
that's the problem. Yeah.
In this problem definition, we are still doing merge sort, but we are using these mathematical operators to reduce our number of steps or something. Is that what you're hinting at, sir?
You will exactly do merge sort. Even let me tell you that no lines of code would change. I mean, very much. I mean, it would not change a lot. Just the only thing is, see, since you are not taking a temporary memory location, right? What you did over here, that's what I'm saying. So you did in the merge algorithm this step, right? If ai less than aj, or let's say a beginning less than a end, something like that. Whenever you are comparing each of these elements, right? You go from here to here and go from here to here. So you have 2 pointers which compares, correct?
Yes,
between
sir.
the elements, and the one which is smaller, you copy that into a temporary memory location. So let's say this is smaller, you copy that into a temporary memory, right? So this is temporary memory, that's what I said, right? And
Right.
then later you copy it back, correct? Now I am saying you cannot use this temporary memory. You have to do whatever you have to do in this array only, that is the in place, right? So if you do in place on the same array and also you use the same array for comparison, getting the point, then how can you do that? Because you just modified the value which you needed for comparison in the next step. So getting the point. So let's say that's what I said. So let's say this is one element and this is one element, and let's say this element is smaller. So apparently, if you just consider one step, if this element is smaller, you have to copy it over here. Correct.
Right.
Correct. But
Right.
if you copy it directly over here, then you are losing this value. In the next iteration, you have to compare this element with the next element which is there. Got it? That's how merge work, right?
Yes, 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 yes.
So once you copy, you are losing the value. But again, you cannot take a temporary memory. So basically, the idea is you have to copy over here, but you have to do that in such a way by using some mathematics, simple mathematics, and that only constitute these symbols. May not be all of them, maybe one or two of them would suffice, right? These symbols and maybe the minimum and maximum value, right? You can use so that whenever you want to copy, okay, you can copy that. But later, if you need this value, the initial value which was there before copying this value over here, if you need the initial value, you can get it when you need it by again doing some mathematics. Simple 1 or 2 line function.
Sir, do we mod it by the position number?
If you make it, I mean, if you mark it by position number, then again you need some location to store that data, right? You would have a bookkeeping work, you need to have it in some memory location. Then that bookkeeping, you would need some extra array or some list to store that. Where do you do the bookkeeping, right? Once you do the bookkeeping, you have to store it somewhere. If you mark it that, okay, my second half's first element would go into this cell as of now. So yeah, I'm not allowing you to have any extra memory location. You have to do merge in place. Fine. So okay, yeah, you want to ask anything more?
No, sir. I'll give this a shot later.
Yeah.
After this.
Okay. So yeah, you can also, if someone comes with any idea, you can also state it on Discord. Fine. Just state it on Discord. That's also fine. If you want to tell in the next session, that's also fine. Okay, so now let's continue with this week's content, and we would start somewhere on the same lines. So in this week, we saw the quick sort. That was the only sort that was not done in the previous week. I mean, not the only sort. There are many kinds of sorts, but in our syllabus, the quick sort is the only sort which is left in week 2 and week 3, and sorry, which was left in week 2 and continued, and we did that in week 3. So my question would be again that I hope most of you have gone through at least the first 2-3 lectures. So my question would be again that what are the disadvantages of merge sort other than the extra space that we had to think about quick sort? Any other disadvantage that you can tell? And mind one thing, that this disadvantage may be an advantage for lesser amount of data, or maybe a disadvantage for greater amount of data, or vice versa, right? Which is kind of solved in quicksort. So what is that disadvantage other than the temporary space? Hello, what happened? No, other than temporary space, no other disadvantage of merge sort? Okay, fine. So tell me one thing. If I have a small set of data, let's say I want to sort an array of or a list, say 2, 7, right? How will merge sort operate? Just walk me through the operations of merge sort.
Sir, it will break it into groups and compare and then remerge them back.
So it would break it like this, then it would break it like this, then it would break it like this, right? And then it would again do the remerging, correct? So it remerges and it's again 2, 7 only. It remerges again, it's 1, 9 only. And then it finally again does a remerge. And then it would be 1, 2, 7, 9. Okay, so can you think how many recursive steps it took to break this? I mean, how many times? So you are going up to the bottom for simple small array. You are going up to the bottom for so many recursive calls. You break it up into 2, 7, here 1, 9. Again another recursive call and then merge call to do this 2, 7, which was already sorted. Mind that this was already sorted. So you wasted this recursive call. You just wasted it. It was not required. Again, you took another recursive call for the same reason. This was again sorted, but you took that and you wasted that recursive call. Finally, this is something valid because yeah, it was unsorted, and then you are doing the comparison and making it. But the point is, in order to do each of this recursive call, sir has mentioned that in the lecture that we need to do some bookkeeping work. Correct? We need to do some bookkeeping work. Sir has mentioned that. That bookkeeping is nothing but some extra memory space for every recursive call. What happens internal to the system is some extra memory space is used up, and that is a huge space. If you do that continuously for a long amount of time, for a sufficiently long amount of time, it can even crash your system. Right. So I don't know how many of you have encountered this in Python course. If you do an infinite loop or maybe call a function infinitely many times, you would see a stack overflow error. Correct? Not a loop, but a function. If you run a function infinitely, you would see a stack overflow error. So things like that. Whenever you call a recursive function, whenever you are doing recursion, then every time there is a system stack. In that system stack, some memory space is taken. Right? I'm not going into the details of that operation, but that is the bookkeeping work that sir was telling about. So basically, whenever you are doing recursion, you are simply using extra space. And that's why whenever we analyze the space complexity is not something that we would analyze greatly in this course, as sir has also said in the introductory lectures, that time complexity is something that we would bother more about. But when you analyze space complexity, not only the extra space like list, array, dictionary that you take is considered, but even for recursive calls, the space taken by each of this recursive call is also considered when you consider the space uh, consumed by a program. Correct. So for small lists, for small collection of data, having so much overhead of bookkeeping and taking extra memory space is something, not only the memory for the extra array that you take in merge, this memory is something more. This is not only the memory which merge sort takes for the array, but also but this is an extra memory space that is considered by the recursive calls, right? That happens because of the recursive calls. So for small arrays, you are doing so much recursion and wasting so much space that was not required, right? So that's why for small collection of data, merge sort is not something which is quite preferable. And even the data, if it is partly sorted, like this in this example, even if it's partly sorted, then also merge sort would go at the end level of breaking it down to the single value, and then again merge the whole thing back. So it's working in an unintelligent manner, right? So that's why for small data, merge sort is, good, but may not be that much good while you compare it with quicksort. But for large amount of data, merge sort is better. Why? Because the overhead of the bookkeeping work that is required, not only with respect to the extra stack space, but in general, right? That is somehow overpowered by the efficiency that you would gain by doing merge sort for large data set. The reason for that is, in a large data set, the worst case time complexity of quicksort can grow up to n square. But in merge sort, it would be theta of n log n. That is, the worst case would always be n log n, best case is also n log n. Correct. So merge sort is better for large data sets in general, and quicksort is better for small data sets in general. Right? I'm speaking in general. One or two cases, obviously, depending upon the input, it would change. But if you run quicksort and merge sort on different sizes of data for a huge number of times, then you would see the average performance of merge sort is better when you have a large data set, and the average performance of quicksort is better when you have a relatively smaller data set. Okay. Is this one point okay? Any questions, any doubt, any contradiction?
No, this is fine, man.
Okay. Fine. So that was one thing. That was one problem with merge sort, and we somehow we don't need that much of bookkeeping work in quicksort, because you just simply do a partition, and the partition algorithm simply puts each element at its proper place. So all elements before that particular element would be smaller, and on the left hand side, and all elements on the right hand side would be larger than that. So how can I see a raise of hands who all understood the partition algorithm? So all of those who understood the partition algorithm properly, please raise your hands. Please keep your hands raised until I say. Okay, fine. And now all of you can, lower your hands. Okay, so now can I see how many of you did not understand it? Raise your hands who did not understand.
The partition algorithm is merge sort, na?
No. Quick sort. Merge sort is merge algorithm, right? Partition is in quick sort.
Actually, we haven't watched the lectures yet, so that's why.
Okay. Okay. So okay. No issues. So I would give a brief brief walkthrough of how partition works, and then I would go into the detail, because the next point of comparison between merge and quicksort is something that would require the understanding of partition algorithm. See, it's very important you understand each and every detail corresponding to the advantage and disadvantage of each algorithm of sorting, because when you are developing something, let's say you later in your journey you do some in web development, or maybe in Android or any kind of development, right? So ultimately at the end of the day, when you have to make a product, it usually depends on what kind of data structure and algorithm you use, and on top of that you use the utility, right? I mean, you want to do web development, you do the web development using the tools provided by JavaScript, HTML, all that is fine. But when you are making products, when you are making systems, right, and not only on the front end, when you are working on back end to develop a product, you have to use data structures and you have to think about techniques, that what should I do, what kind of algorithm I should implement in order to do something, right? So you should understand the advantage and disadvantage depending upon the use cases. Now, what are the use cases? Use cases can be the size of the data, the property of the data, right? A data set can be very much sparse, and also you all are also going to learn in the data science, right? So you should have ideas of sparse data, concentrated data, where the variance is more, where the standard deviation is less, or something like that, right? There are many aspects of data. So whenever you try to choose a particular algorithm to work on a specific data, there are two very important points: is what is the underlying data structure, and second important point is what is the property of the data that I'm going to work upon. Is the data very much huge, or is it considerably small? Depending upon that, you can just change your algorithm, and that would give you a better results on a long run, right? One or two run of the code doesn't matter, because that just, I mean, any algorithm would give you a good result in one case. That might be the best case for that. But what you have to think about is what would be the average case when you run it for, let's say, 1 crore times. So you have to decide which algorithm to choose. So I would now just discuss the partition algorithm, and then we would go into the second point of comparison between quick and merge sort. Okay, so before that, Akash, you want to say something? You have not lowered your hand.
No, sir, I forgot to lower it.
Okay, fine. So this is the partition algorithm of quick sort. So partition says, okay, I would give you a skeletal structure of how quicksort works. So let's say this is my partition algorithm. I'm not passing the arguments, huh? Just assume those things are there, the list and all. Now here you would have the quicksort. The list and index and all, start, end. Okay. The only difference between the basic structure of quicksort and merge sort is, here also you would do divide and conquer. I mean, oh, sorry, I used the term mistakenly. Don't think about divide and conquer. Okay, we would discuss that later. But basically, quicksort and merge sort, all these algorithms are parts of a algorithmic tool which we call divide and conquer, right? But we would discuss that later. So basically, the structure, if you see the code structure of quicksort and merge sort, it's kind of same. The difference is that I'm writing, see, here also you would do the if check, that whether beginning is less than end or not, right? That is basically whether you are inside the array or not. And then what you do is you call a function called partition. What that does is, I would come to that later, right? Partition, and you pass the list and the start, end and all that. I mean, beginning, end and all that. Fine. And after that, what you do is you recursively call, just like merge sort had that recursive calls, right? From the left half and the right half, beginning to middle and middle to end, 2 calls, and then you did the merge. Here we do the partition first, and then we do the recursion, right? And why it is so, I'm telling you. The reason for that is the partition returns a index value which is k, and now we would break the array depending upon the k value. I mean, k is an index in the list or array, right? Now the breaking in merge sort was exactly into two equal halves by 2, right, in middle. But the breaking in quick sort would be from beginning to the kth index and from k plus 1th index to the last. Got it? It's not two equal halves. It's two. It may be equal if k is at the middle, but it may not be equal, right? So I do a break from beginning to k, and then I again call quick short, and that break would be from k plus 1 to end. Fine. So this is my quick short. Yeah, you want to say something?
So merge sort is a special case of quick sort.
You can say it like that. I mean, I would not very much support that, but yeah, understanding wise, it's something like that. Yeah, you can say that, because merge sort is a special case of quick sort when the middle element, I mean, when the array is broken up into two equal halves, always. See, the only point I'm saying that I'm a little bit worrying about telling it's a special case is, see, the partition algorithm is something that is totally different from the merge algorithm. But if you consider only this part, then you can obviously say that merge sort is a special case of quick sort. So you're right about that. Only reason I'm a little bit hesitant to call the general, I mean, quick sort as a general case of merge sort is because the way partition algorithm works. Partition algorithm is totally different from the merge algorithm. Huh. Yeah, this part, yeah, okay. It's a general case. I mean, quick sort is a general case and merge sort is a special case. Fine. Okay, so now the partition. This is just like merge sort, right? Only thing is that in merge sort we had it merge over here. The merge was over here, and the breaking was, this breaking was not at k but at the middle. That's it. Fine. So this is the basic structure. Now let's come into the partition algorithm. So I would draw the, I would do a dry run first, right? How it works. Okay. So suppose this is the initial state of the list or array that we are considering, and my I would have two pointers. Pointers means two variables or two markers that would point over here. One would point over here, other would point at the -1th index. That just, you can just set it to -1. Okay, I equal to -1, j equal to L of 0, or I'm not L of 0, I mean j equal to 0. So j is equal to 0, I is equal to -1. Fine. This is wrong. Yeah, I equal to -1. Now what we will do is, the partition algorithm is based upon picking up a pivot element. Now what do we mean by pivot element? As the name suggests, pivot is something which is fixed. I mean, you consider that, and as compared to that, you consider the other elements, right? Something which is fixed, that is the holding point. Now pivot element can be any element in your array or your list. Whenever I say array or list, just consider both of them interchangeably. So pivot element can be any element in the list. But in our lecture, sir has used the pivot element to be the first element. Fine. So as I said, whenever you are considering the pivot element, you would start the partition algorithm from the leftover other elements. Understood? Because this is your pivot. So sir has explained by taking the first element as the pivot element, and that's why sir has used the markers from the second element. So I would be at minus, let's say I points over here just before that. Since now I do not need -1. And j points at 1 is okay. Right. So this was the pivot. In this scenario, this is the way we should do the initialization. But if I consider some other pivot, let's say I consider the last element as the pivot, right? Then again, we would go back to the previous case where I was at -1 and j was at 0. Okay, considering this is the pivot. So since sir has used the first element as the pivot in the lecture has explained it, I am using the last element. That way both ways would be covered. You can also use any middle element, right? And that is an activity for all of you. You can check after you understand the algorithm. Just check what happens if I use some middle element as the pivot and work accordingly. Okay, so I'm considering the last element as the pivot. So this is how we would start. J equal to j at 0 and I would be at -1. Now how this works is you would compare the jth element with the last element, which is the pivot element. In case of the pivot being the first element, you would compare the jth element with the first element. I mean with the pivot. Fine. So in this case, I compare 7 and 3, right? And I see which one is smaller and which one is larger. Now our motive is to sort it in ascending order. So if we want to sort it in ascending order, right? What you have to do is if you see a value which is lesser than the pivot, understand this, if you see a value which is lesser than the pivot, you would shift all such value towards the left hand side, right? Because those values are lesser. So basically, if I give an overview of how this code would, how this algorithm would work is, you would move along the array. Sorry, you would move along the array in this direction. You would check each element whether that is smaller than the pivot element or not. If that is smaller than the pivot element, you would shift that to the left hand side. Fine, you would shift that to the left hand side. And once you shift all the elements which are smaller than the pivot element to the left hand side, right? So basically, let's say this is the place where all the smaller elements from the pivot are, has been moved on the left hand side, correct? So all the elements over here are smaller, lesser than the pivot. After I iterate till the last of the array. So I can say that, and all these elements over here left over are greater than the pivot. Fine. Please mind one thing, these are not sorted. I am not checking for so in insertion sort, what we did, we picked an element and we copied it on the left hand, moved it on the left hand side into its appropriate position. Here we just don't want to do that. Our only work is we would see whether it is lesser than the pivot and dump it on the left hand side. If there are much lesser element on left hand side already, I do not need to compare. Okay, we would run through the algorithm and you would understand what I mean. But the basic idea is once the partition algorithm is over for the pivot 3, last element, right? So all elements lesser than the pivot would be on left hand side, all elements greater than the pivot would be on the right hand side, and none of this may be sorted. All of this is not sorted and this is also not sorted. Maybe, or maybe it can be sorted, but that is something which we are not doing.
That will appear as it is in the original list, just taking care of less than or greater than.
Exactly. And once that is done, what we would do is we would simply copy the pivot element at this middle position. So what we can guarantee after this, we have a list where we have the pivot element at its proper position, all elements lesser than the pivot over here, all elements greater than the pivot over here. So one thing that I can guarantee after the partition algorithm terminates one time for this pivot, is that the last element, the pivot element, is placed at its proper position. So got the point. So it is placed in its proper position. So anything which is on the left hand side of the pivot element would remain on the left hand side, but the order may change. So anything over here, the order may change.
Yes, so index of 3 will be fixed now.
Exactly. Order may change in sorted or in sorted list, but bound to be on left side of 3. And same for here. Only thing is order may change in sorted list, but bound to be on right side of 3. I would, after the partition for 3 is over, I would not copy any element from here to here or here to here. That is not done. So partition algorithm guarantees you that. So this was the overall idea. Now let's have a quick dry run. Okay, fine. So first is 7. Compare that with 3, right? 3 is lesser or greater, 3 is lesser. So when 7 is more, right? I told you when it is lesser, we would throw it on the left hand side. But 7 is already greater than 3. So what we would do is we would only proceed. So my J would proceed over here. Okay, J comes over here. I is at -1 only, huh? J comes over here. Now J see 0 and 3. Now I see 0 is lesser than 3. Correct. When you see 0 is lesser than 3, what you would do is you would dump it on the left hand side, remember? So now what you would do is you would point the I on 7, that is you would draw I equal to I plus 1 in code, and you would swap the a ith element with the a jth element. Fine. So what happens over here is once I find that the jth element, which is 0 in this case, is lesser than the pivot, I would increment I by 1, which was on left hand side, and that's my motive, right? I would throw everything on the left hand side. I would increment I by 1 and I would swap ai and aj. So what would be the state of the array after this? It would be 0, 7. So this is the state of the array or list. Now this repeats. Now we compared up to 0, right? 0 was at this index. Now 7 is at that position, right? So now we compare it with one wrong, 7, right? Yeah, 0 you compared, yeah, you swapped it with 0 and 7, right? Now we compare it with 9. 7 was already done, right? Because this swapped. Now I compare with the next index, which is 9. So my J is at 9. So I see J with 3. This is my pivot, right? 9 is again greater. 9 is greater than 3. So simply proceed to the next 1. Now 1 is lesser than 3. Where was I? You remember? I was over here, right? I was -1. We made I equal to I plus 1. So I came over here and then we swapped between J and I. Correct. So I is located over here currently. And J is at 1. I is at 0. Fine. Now, when you see that 1 is lesser than 3, you remember this code? Again, you do I equal to I plus 1 because you have to swap. So now I moves over here at 7. Fine. And you swap I with J. So your array now becomes 0, 1, 9 remains at its position, 7 comes over here, 4, 6, 2, 3. Fine. What would be the next iteration then? We were at at this position, right? J was at this position with 1, for which we have swapped 7. So J was over here. Now we move J to the next one, which is at 4. Now is 4 lesser than 3? No. So again proceed. When it is not lesser, just proceed. Is 6 lesser than 3? No. So proceed again. Is 2 lesser than 3? Yeah. So again we got 1, 2, which is lesser than 3, and my I was where? I was initially at the second, in the second element, right? I was over here. Again I equal to I plus 1, because 2 is now lesser than 3, I would have to swap. Before swapping, I need I equal to I plus 1. So now I comes from 1 to 9, from here to here. Right? Now again swap 9 with J, I with J. So my array becomes 0, 1, 2, 7, 4, 6, 9, and finally 3. Now you see 0, 1, 2 is done. Where is my I currently? I is at the third value, right? The third element, which is 2 in this case. Right? And J has finished. This is the pivot. Pivot we don't consider. J has finished its operation. Right? Now what you will do is see, since J has terminated its work, now what you have to do is simply place 3. Once the J terminates, that is it exhausts the whole list, it travels the whole list, you would simply do I plus 1 and put the pivot element over there. Because all the elements which were smaller, we have swapped it on the left hand side. So if I simply do that, 0, 1, 2, I do I plus 1. So that would make it to point at 7th position. I would put 3 over here, 4 over here, 6 over here, 9 over here, and 7 is swapped. So this is your result of partition. Fine. Now you see, so you have placed 3 at a position. See, on the right hand side, there is no element which is lesser than 3. On the left hand side, there is no element which is greater than 3. We got lucky because we got a sorted order over here. See? And here we got unsorted. But one thing is very important, none of the element on the right hand side is smaller than, is lesser than 3, which is the pivot, and none of the element on the left hand side is greater than 3, which is the pivot. Right? So that was the idea. You may get sorted or you may get unsorted values, but one thing is common, one thing is for sure, that all values which are greater than 3 would be on the right hand side, and all values which are lesser than 3 would be on the left hand side. This code is fairly simple, right? You just have to run a loop, have the values I and j, compare the value, proceed j one by one. Whenever you see a greater value, you proceed. Whenever you see a lesser value than the pivot, increment I by 1 and swap the value. At the end of the loop, when you have iterated throughout the list, right, what you have to do is just swap the I plus 1 with the pivot element. That's it. That's the partition algorithm. Simple. Traversing a list and swapping the elements when you see a value which is lesser than the pivot. Okay. So what does it guarantee? And okay, so another thing, what the partition algorithm returns is the index position of this value. Because now you know this value, the index of this value. And that is 0, 1, 2, 3. In this case, the index is also 3. The k would be actually 3. Right. So why is it so? Because we told you that the sortedness is not guaranteed. It can be unsorted. As you can see on the right hand side, it's unsorted. So once partition is over here in the code and it returns k, which is k equal to the index value. So what you have left with is this unsorted part and this unsorted part. In this case, it is sorted, but that is totally, it may not happen, right? So these two unsorted part you will get. So now you have to call quickshot on these two parts separately. That is our recursion, right? So this is the same case. See, quickshot from beginning to k and k plus 1 to end. Fine. So this is the partition algorithm and the quickshot, how it works. Any doubt?
Can you please explain code of quick sort with one example how it's works? So there I have understand that how it works, but in code just I'm confused.
Okay, so you understood the basic thing that I discussed now. Did you understand that?
Yeah.
I mean, the dry run of it, whatever we explained over here, did you understand that properly?
Yeah, sir.
Now I would explain on the code itself, not in detail, but since same thing, sir has also given the example. Only thing is the pivot he has considered to be the first element. I considered it to be the last, so that both types you should be aware of. That's it. You should get to know. So if you see, this is the code of quick sort, and it's just like the thing that I said you. So see, basically this is your partition. This part of the code now, if you see, yeah, before the recursive calls, this is your partition algorithm. Sir has given that in a single quick sort function. Okay, so okay, so this part, if you see, I told you now, see, quick sort L to lower and quick sort lower plus 1 to upper, right? Who is setting the value of lower? See, this part is setting the value of lower, correct? You see lower plus 1, this lines, right? This line. So basically this part of the code is setting the value of lower, and in the example that I discussed, I just made it into a separate function, which is the partition function, because conventionally this part of the code which is currently highlighted on the screen is the algorithm which we call partition algorithm. Fine. Sir has merged it into a single function and explained, taught all of us. So this is the partition algorithm. Now just see how the code is working, just this part. See, pivot lower and upper, just like the beginning and then the pivot. Now see, pivot, sir is setting it to be the first element, right? And then he is proceeding. I just considered it to be the last element. You want to say something?
Sir, you want it to be L of 0. It's L of 1.
No, this is a marker, no? I mean, you can consider it to be anything. Sir is considering the pivot name to be here.
Okay.
Right, this one. So you see here it is starting for I in range L plus 1 to R. R is the last, I mean, at the upper limit value, right? Where you are going, when you are inside the call of quick sort, R is the last index, last value, L is the lower index where it starts. So it's starting from L to R minus 1, L plus 1 to R minus 1 up to, this is the range of the loop that we are going. Why R minus 1? Because obviously you are considering 1 as pivot, right? So you would not need to, you would need 1 less value, right? And that's why you are starting it from L plus 1 also. The same thing that I told you. We do not consider the pivot, we consider it from the next element, right? So let me just again restate it. What Sir has done over here is, Sir has considered this element as the marking element, and then he has started from over here, right? Like this, compared all of these, and then swapped at the appropriate position. And then if you see if Li is greater than pivot, I said what you have to do is simply go ahead. Remember when we were over here, if 4 is lesser than 3, no, so we move to 6. If 6 is lesser than 3, no, we move to 2. Whenever it is not lesser, we move to the next index, correct? That is, we increase our upper limit by 1. Same thing, right? We say upper equal to upper plus 1 if it is greater than the pivot. If it is lesser than the pivot, then what we used to do, we used to increment the initial value and then swap it. Remember, I equal to I plus 1 and then swap it.
So it should be less than or equal to.
That depends on your implementation, right? You can, I mean,
No, suppose if they are, I mean, it's There are multiple common elements.
Okay, yeah, you can do that. You can do li greater than equal to pivot. I mean, you can do that, no issues. Fine. Anyway, I mean, if it is greater than equal to pivot, or I mean, if you keep that only greater than, put the equal to over here. Right. So here you do else exchange li with start of upper segment. See, right? Upper segment means the if. Remember, it was pointing initially. We increased it by 1 and then exchange that. So you just do that exchange, and at the end of the day, when the whole shift both segments by 1 element up, you do j plus 1, I plus 1, and at the end of the day, when you have when you have done the whole thing, then you do you just when you end up all the recursive calls, you just simply at the end of the recursive call, you place the pivot at its proper position. That's it. Same thing. So basically, the confusion is here because I discussed it in the form of that partition algorithm, but this is sir has given that in the form of the same. I mean, why it's not getting highlighted? I mean, over here.
Sir, one question, sir. Sir, here lower and upper is considered as I and J. So why it is taken L plus 1 and L plus 1, like we have taken in previous, we explained that I is -1, then J is 0.
Yeah,
Means
exactly.
we
I
are
told
taking
you
next
that.
element.
Correct. I told you that. So let's say I considered the last element as pivot. Correct. So I had to start my search from here, from the first element itself. So if I have to start my search from the first element itself, I would keep my other marker. I mean, the marker which is behind. So two markers, right? This is one marker. This is one marker. The first marker proceeds through the whole list. The second marker only stays at the position where you have to make the next step. Right? Try to see this. The J marker proceeds on the right hand side. The I marker always remains at the position where you have to swap the next element when you find one. Right? Got it? So when I'm doing that from the first and considering the last element as pivot, so I start my search from the first element itself. In that case, I have to keep my I behind J, correct? So that's why I'm setting it to be -1. And later I do I equal to I plus 1, so it becomes 0. And then I do the swap. But if I start from the first element itself, now, if I make it pivot, if I make this one pivot, fine. Then what happens? Then I have to start the test from here, from L1, right? And I would set I would not require -1 anymore. I can set it to be 0. I can do +1 and swap it.
Then sir, I and J will be both L of 1, right sir?
What? I and J would be?
The first element.
No, you are doing +1, right? You can set I to be 0. That totally depends on your implementation. Only thing is you should keep I behind J.
Sir, as first element is pivot element, so the next element will be considered as I and J in this.
If you want to do that, then you have to also again consider when you do I equal to I plus 1, it would be +1, right? Consider that before the swap. If you make both 0, if you make both marker I and J to be at the 0th place, then also you have to consider when you do I equal to I plus 1, because in that case it would become I would move forward to J, right? If J would remain here, I would move here, because I equal to I plus 1 is done once, right? So it's better to keep
that means,
one behind. Yeah,
that means sir, always I should be one step behind J.
One step behind J. Fine.
Yes sir.
Now you can think of it from the other way. Let's say you start your search from here, right? So in that case, I would be one step ahead of J, right? I would point over here, J would point over here. Why? Because you are proceeding in this way, and you would check each element, and J would proceed like this. Whenever it finds one element to swap, it would swap with the last position where I is present. Okay, so the idea is there would be two markers, it doesn't matter. It totally depends on your implementation from which direction to start or which pivot to consider. Only idea is one marker would be behind the other one. You can call it I, J, lower, upper, whatever. One marker would be behind the other one. The first marker which is ahead would travel the leftover part of the list, and the marker which was behind would stay at a position where you can make the next swap if required. So whenever the marker which is traveling ahead finds a value suitable to swap, suitable means if you are sorting in ascending order, then a value which is lesser than the pivot. Whenever the ahead marker finds such a value, it would simply increment the marker which was behind by 1 and simply make the swap. That's the idea. Fine. Okay. Now, in whichever way you want to implement, you can implement that. So we are just learning algorithms, right? So algorithm is important thing. Implementation is totally left over to you, how you want to do that. Okay, so the next part is, so you understood the partition algorithm, the main part of it. Now again, I'm coming back to, okay.
In this
yeah.
list,
What happened?
Scroll. Please scroll the sheet, sir.
Scroll, okay.
Wait. Yes, sir. More, sir.
Yeah.
Here, sir, we have looked that the 7 is our pivot.
Sorry,
And,
can you speak a little louder? I'm not hearing.
So here in this list, 7 is our pivot.
Sorry, is it the problem with me or can anyone else?
He's saying 7 is the pivot.
Okay, fine.
Yes, sir. And lower and upper is 1, and lower is 1 and upper is 1. Then we will go next 0, and we will compare the pivot that it is greater or less.
Okay.
Yes, sir. Then I have seen that 0 is less.
Yeah. Then
So
you would do
what
a simple again swap with 0 itself. Or you would actually move, if you do I plus 1, you would move to 9 and then swap 0 with 9. Understood what I'm saying? The problem, if you start from 0 as the element where both lower and upper or I or j points to 0 itself, when I consider 7 as the pivot, so when you do the swap, you compare 0 and 7, you see 0 is lesser than 7. Correct? So what you would do? You would do I plus 1 and then do the swap, correct? So where would I plus 1 take I? It would take I to 9. Correct? Because it is at 0, right? When you do I plus 1, it would go to the 9, right?
Yes, sir.
And then you swap 0 and 9, that means. Is that something that we want to do?
Yes, sir. Then we will compare 9 to pivot with pivot.
No, I mean, see, that's what I'm saying. If you start from the, always keep, so it's better you keep in mind as of now, just take one element, I mean, one marker ahead and other marker behind. Do not start it from the same element. If you started from the same element, you have to take care of the I plus 1 thing, that when you do the plus 1, you don't move it to the next element. Always, as of now, just keep in mind, you start one marker which is behind. I mean, do not consider both of them at the same spot. That would be easier for you to code. I'm not saying that is the only way out. You can always start from the same element, but you have to take care of the I plus 1 in that case. Okay. See the point, are you not getting? If you have I and j at the 0th position, right? What will you compare 0 with 7? You see 0 is lesser than 7. You would have to swap, right? What will you swap? With whom will you swap?
We will swap 0 with itself, sir.
With?
We will swap 0 with itself, because
exactly.
lower is 1.
Okay, so you swap 0 with itself, fine. So that means you have not executed this line of code. I plus 1 you have not done, correct? You have directly swapped AIAJ.
Yes.
Fine. Then let's proceed in that way, huh? Let's see what happens if we proceed in that way. Okay, you swap 0 with 0. Then you move.
Then sir, lower and upper will be 2.
Okay, so so upper is pointing over here. Upper.
Yes, sir.
Okay, I'm writing by U and L, huh? U and L. So U points over here.
Yes, sir.
And your lower was over here. Yeah, after that?
No, sir. Lower will also at 2.
You would move lower along with it. Right?
Sir. Yes, sir.
Okay, fine. Now, yeah, that is another way. This also you can do. But okay, you continue till. If you move lower along with it, then what happens?
Then it is higher than pivot. Then
Fine.
upper will 3. It means that 1.
Upper will?
3, sir. Upper will plus 1.
Upper goes over here.
It
Okay,
will
fine.
go here. Yes, sir.
Okay,
Then
then
we will compare 1 with 7. And it is the less than 7. It means we will swap with lower.
yeah. So now you are not doing plus 1, right? I mean, you are swapping 1 with 9, correct?
Yes, sir.
Yeah.
1.
But you did the plus 1. I mean, you did the. You moved the lower as well when you did the first swap, correct? Because when you
Yes,
moved
sir.
from 0 to 9, you did the you moved the lower as well with the upper, correct?
Yes, sir.
So upper was here, lower was here. You did yourself the swap with itself, and then you move both upper and lower over here.
Yes,
And
sir.
then when you are now comparing, then you need not move the lower at first. That is other way. That also you can do. But in that case, you have to keep in mind when you move with itself also, you move the lower along with the upper. Right? That is another way. You can do that. Or you can move the upper every step, place the lower at a specific position. Whenever only the swap happens, you can move the lower plus 1 at first and then swap. Whatever you are saying is doing the swap, then doing plus 1. Whatever algorithm I said is doing plus 1 and then doing swap. So this difference is there. That's why I said it's better to follow only one. Okay, you have to do a plus 1, and that plus 1 may happen when you swap it, before swap it, or you after swap it. But don't mix both of them. Fine. This is also okay. This also would work. But you should not again move. I mean, you should always move the lower in this case whenever you do a swap. Okay. Before the, I mean, after the swap. Whatever you said is after the swap. Whatever I said was before the swap. What's the point? Again, this is again implementation dependent. Whatever implementation you think you can do. Fine.
Sir, is it necessary to take lower and upper from beginning only?
No. I mean, that's what I said, right? You can start from right hand side. I mean, you can also set, let's say, you say take upper over here, lower over here, and take this as pivot. No issue.
Okay, sir.
Or, I mean, you can also start upper over here, lower over here at the outside, the way that I was saying, -1 and then proceed one by one. Anything. Only thing is, please keep in mind that plus 1 thing. You can do the, as I don't know your name, whoever said that. You actually move the lower along with the upper after the swap. The algorithm that I discussed moves the lower at first and then does the swap. Fine. Both of them works correctly, but don't intermix both of them. Then it would be a wrong approach. Fine. Whichever way you like, you can code.
Okay, sir.
Yeah. So, okay, sir has actually mentioned quicksort uses divide and conquer like merge sort. As I mean, we are basically dividing the array into subparts and then sorting it. Now, analysis of quicksort. Before going to that, what do you think is the worst case time complexity of quicksort? Acha, what was the worst case complexity of merge sort?
N log n, right?
N?
Log n, right?
N, sorry, repeat.
A log n.
Hello? Can you please repeat?
N log n?
Okay, I can't hear any answer. It's N.
It's n square.
O n square, sir. N square. Worst case will O n square, and average and best case will be n log n. Am I audible, sir?
Yeah, yeah. So the worst case for quick sort is order of n square. Right?
Yes.
Now, why is it so? In merge sort, what was happening is if we have an array, right? If we have an array, we were always dividing it into two equal parts. Right? So every time how many steps we need to do in order to break an array of size n, right, up to the level of size 1, right? If we
Sir,
break it every time into 2.
Could you please check graded assignment 2, question 3?
What?
Graded assignment 2, question 3.
Okay.
Here it says, in every case, best, average, worst, time complexity of merge sort
Yeah.
is n log n.
Okay.
I mean, for each scenario. Is that correct or wrong? Could you please take a look?
Graded assignment for this week, right? Then I cannot ask you, I will tell you anything about that.
Week 2 graded assignment.
Okay, week 2 graded assignment. Right?
Question 3.
Okay. Wait a minute. Acha, can you tell me at this end? I mean, I would consider them at the end, right? I'm just.
No, it says,
yeah.
Since merge sort always divides the array into two halves
Okay.
and takes linear time to merge two halves,
okay.
That is why in every case, best, average, worst,
Yeah.
time complexity is the same. That is
Yeah.
O n log n.
Yeah.
But
yeah.
Here we are saying the worst case is O n square for merge sort.
Who is
That is for quick sort.
That is for quick sort, right? I've written worst case quick sort is
Okay. I mean, while you were speaking, I heard merge sort worst case is O n square.
No. Must. That's what I discussed in the first part, right? Whatever you give, merge sort will break it down to the basic level, and that's why it's always n log n.
Yes.
Fine. So how many
Sorry.
steps, if we break it down, then how many steps we need if we do it by 2 times? So let's say we need to break n k times. I'm breaking n into 2 equal parts, k number of times. So halving by once, then again halving, then again halving. So I do it for k number of times in order to reach at a single element, right? So if I just solve this, it becomes n equal to 2 to the power k, and if I take a log raised to n, then I get value as k. So this is my value. So I need to half the array or list log n times in order to break it into a single element. Fine. So that's why you saw merge sort, the recursive call of merge which was going on takes log n number of steps to break it down into a single element and then work upon it. And n is the time corresponding to the merge algorithm that you are just telling about. Fine. So this is decomposing or dividing part, and this is the merge algorithm. I hope it should be clear now. And then why in quick sort are we saying that it's order of n square? See, the reason for that is in quick sort we are not dividing it into equal halves, correct? What we are rather doing is we are just finding the pivot elements proper position, and we are taking the left array and right array and putting that into recursive calls for quickshot. So what happens if the pivot element's correct position is the last element itself? I mean, what happens if you put an array which is, let's say, you consider the last element as the pivot element, right? And you are doing a sorting in ascending order, fine? And the array that you have given is already sorted. Okay, so 1, 2, 3, 4, let's say 5 was there over here. Right, 5 was over here. You choose the last element as the pivot element and pass this array in the quickshot. What would happen? It would pick the fifth element as the pivot. It would do the partition algorithm, which would take order of n time partition. And at the end of the partition algorithm, it would see that 5 should be placed in the position where it was already placed. That is, it is the last element, because all elements are lesser than that, and that should be on the left hand side. So when you give a already sorted array in the order, ascending order only, considering your quickshot is also sorting in ascending order, if you give such an array as input, what would happen is every time the two parts of the array after the partition algorithm is over would be of size n-1 and 1. Got the idea? I mean, not every time. I mean, if you do that, first iteration, it's over here. Let's again say if you consider the last element as pivot, which is 4 over here, then again it would be at it's already in its correct position, right? So again, this is the n-1 part, and this is the 1 part. Then if you consider this is the pivot later, then again this is the n-1 part, and this is the 1 part. So every time it is always dividing the array not into two parts. It is dividing the array into two parts, in which one part is of length n-1 and the other part is of length 1. Got the idea? In merge sort, it was dividing into n/2, n/2. In normal quick sort, in general cases, it can divide into n/3 and let's say 2n/3. That is one division. It can divide into n/4 and let's say 3n/4 or whatever. I mean, any possible division, right? n/2, direct n/2, n/2 is also okay. So any possible, depending upon where you are placing the pivot in its correct position, right? These are the possible ways you can divide the array in quickshot. But one possible way among these is n-1 and 1, considering that always the pivot element's correct position to place is at the last only, right? So in that case, the left hand side sub part of the array would be of length n-1 and the right hand side would be of length 1. In this situation, I am not getting this divided by 2 or divided by any constant factor, right? It is actually getting subtracted by 1 in each call. n-1, then again n-1, just the worst case that I just showed you. Every time it would be 1 lesser, 1 lesser, 1 lesser. So if I do n-1, n-1, then how many times I have to do in order to reach to single element, right? Then I have to do it for n number of times, right? n-1, then again n-1 dot 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 dot. I have to do it for n times, right? Actually n-1 times. So let's say consider order of n times in order to reach a single element. So your decomposition over here is for order of n, and your partition algorithm was also taking order of n, right? And that's why here it is actually n into n, that is n square. So the worst case scenario for quick short is when you have a recurrence of something like this. This is the time for your partition algorithm, fine, and this is the recurrence. I mean, the recursive call for quick short. Okay, So when your pivot is already placed in its correct position and it is located at one end of the list or array, then you are actually in the worst case of quickshort. Another example of bad case of quickshort can be when you have all the elements as same. Right. So if you consider this as the pivot, let's say then this is at its correct position. When you consider this in the next half, then again it is in its correct position. So already sorted array, same elements array, these things are the worst case for quickshort. Fine. Now,
Sir, I have a quick doubt.
Yeah, please.
Sir, in your example of 1, 2, 3, 4, 5,
Yeah.
if my pivot element was 3, then would the worst case still be order of
No,
n square?
No. Will it be order of n square? If your worst case is 3, then your subparts would be this and this. Then what is your recurrence? Your recurrence is not n minus 1 and 1. Your recurrence would be something like t of n equal to, actually it is exactly dividing by 2. So your recurrence would be t of n by 2 plus t of n by 2 plus order of n for partition. If you solve this recurrence, this is actually your merge sorts recurrence, correct?
Yes, sir.
Yeah. So every time you do that, it totally depends on the, the pivot that you are choosing and the input that you are giving. Right. So quickshot, there are two factors which decides the game: the pivot that you are choosing and the input that you are giving. Right. Try to understand. Now you have chosen 3. So in that case, what happens? Your two subparts of the array would be left is 1, 2 and right is 4, 5. It's not, in that case, your array is getting divided by, not by 1. The two subparts are not of length n minus 1 and 1. It's actually n by 2, n by 2. Right. Approximately.
So for the same input, it can be either n log n or n square also.
Exactly.
It's a basis how you choose the pivot.
Exactly.
The strategy to choose the pivot. Then there should be some strategy to choose the pivot also.
Exactly. Whether, so that great question. So whether there is a strategy to choose the pivot. Now, if I say you 1, 2, 3, 4, 5, if you choose the last element as the pivot, then it's giving you the worst case n square. And if you choose the middle element, it's giving you the best case, which is equivalent to merge sort, which is n log n. Correct? So whether there is a strategy to choose the pivot. If you choose any strategy, then there would be some other input case that would behave badly corresponding to that strategy. Isn't it? Right? If you choose the middle element, now this is again a very interesting part. If you choose the middle element, I can always come up with an array such that the middle element is the element which would be placed at last. Let me tell what I mean. Let's say I give you 1, 2, 3, 4, 5 only. 1, 2, 5, 4, 3. You choose the middle element as the pivot. Fine. What would happen? You would end up with something like this. This may change. This can be 1, 2, 3, 4 or whatever. You would end up with something like this. So your unsorted part is this one, and this is your the pivot part. So this is n1, this is n minus 1. So you again arrive at the bad case, which we discussed over here. Right. So same example with the same elements, I just changed it. The input I changed. You are taking the middle as the pivot. So this is my worst case again. Right. So whether you any strategy of choosing the pivot, there would be a corresponding bad case that would actually make your complexity order of n square. So what to do? How to tackle with that? So that we have not discussed in detail how to tackle with that. That is what what we do is basically we choose the pivot randomly. So in one run we choose, let's say, the last element as pivot. In the second run of the same corresponding to the same input only, we are calling recursively. See, we are calling here recursively, right? Quickshot, quickshot. So in one call of quickshot, we would consider the last element as pivot. In the, let's say, in the subsequent recursive call, we consider the middle element as pivot. In the next call, maybe we can consider some other element as pivot. So if we do that, then what we do is we average out the probability of getting into a bad case. Right? So your strategy of choosing the pivot changes depending upon the input. The input is also variable, the strategy is also variable. You keep both of them variable, you get an average case. So that is what we call randomized choosing of pivot or randomized quicksort.
Sir, so for the first iteration, we choose the last element. Second iteration, we choose the first element. And the third iteration, we choose the middle element. And we keep going in this order. Is that what you mean?
Yeah, I mean, that's randomized. You can do it in any order. I mean, you can also just pick randomly. I take the fourth element as the first pivot in the first recursive call. I take the first element as pivot in the second recursive call. Right, that is randomized. I mean, you can take that, you can follow any specific order also. Only thing is you do not keep choosing the pivot as a fixed value. That would actually average out the probabilities of getting into a bad case. Fine. Yeah, so that is one thing. And also, if you can always guarantee that you find the median element as the pivot, right? So that is also discussed. If you can always guarantee that I find the median element as the pivot element, that is, I choose the element as pivot, which is the median element, that is, it would always be placed in the middle. Then basically you would gain the best case, that is order of n log n, which is equivalent to merge sort. Fine. But again, I'm mentioning the fact merge sort is somewhat more not so much space optimized when you are considering small set of data. So you do not need to go into so much of bookkeeping. So that's why the name quicksort is used. I mean, when you have lesser amount of data, prefer quicksort over merge sort. Just don't see that whether the complexity is n square. So I should always use merge sort because I can guarantee you n log n. Complexity is n square is fine, but if you have lesser amount of data, the n square value would also be lesser. That will be insignificant, right? For smaller value, n square and n log n may not be that much computationally different. I mean, they will not be so much different in magnitude. Rather, if you use more memory because of merge sort, because of the stack and multiple bookkeeping work, that would be not so much good, right? So these points are very important. When you have small set of data, prefer quicksort. Although it may run into the worst case of n square, but that n square would be small because n is small here. The data set is small itself. But if you have a large set of data, then always try to prefer merge sort. In general, there may be specific requirements, but in general, merge sort. Okay, so worst case of quicksort done. One more important point. So this comes. So quicksort can divide in any size, right? It can be in the middle. It can be 1/3, 2/3, all things, right? So if I have, let's say, two quicksort divisions, that is, the pivot element is placed in such a position that the two left and right arrays, the subparts of the arrays, are of different sizes. And let's say the first call of quicksort divided the array into size, let's say 2n/3 plus t of n/3 plus partition order of n. And here it's, let's say, divided it into n/2 plus, let's say, tn/2. Again plus order of n, right? So what would be the complexity of both these cases? What would be the complexity?
N log n?
Yeah. In both cases, it would be n log n.
Sir,
Why?
how can you please explain?
Yeah. See, this is very important. This is n log n, that is understood. Fine. But how this is n log n? See,
L log 3n will be, it will become a factor.
Exactly. So here it was 2, right? Because we were dividing by 2. Basically, this complexity, we can write something as, I'm just marking star and writing over here. You can write something as order of, let's say, n Sorry, mistake. It should be actually 3 by 2. Why I considered this part? And see, I'm writing the complexity of this one. Huh? Now I have a question. This is one part of the array. Let's say this is the left part of the pivot, and let's say this is the right part of the pivot. Okay, for others also, got it right what I'm saying? So let's say this is the array. You put the pivot over here. This part of the array, which is over here, that is the larger part. Let's say this is the smaller part. Just a second. Redraw it. So this is the larger part, huh? So this size would be 2n by 3. This is the smaller part. This is n by 3. This is the element after the partition, that is the pivot element placed at its proper position. Pivot placed at its proper position.
So somewhere -1 should come in either of the parts.
Sorry, can you repeat?
I mean, either it will be 2n by 3 minus 1 or n by 3 minus 1 because of one element being pivot.
Yeah, I mean, yeah, -1 means, okay, just a second, just bear with me, I would tell this. So this is 2n by 3, this is n by 3, right? Now in worst case complexity, what we do, we consider the part which would take the maximum amount of time. Correct. Now, which part would actually continue more number of recursive calls? This part or this part? Obviously, the part which is greater in size, right? Because in order to break that into a single element, I have to run the recursive calls more number of times. So my 2n by 3 part would actually run for more number of recursive calls, but my n by 3 would be over before only. In this case, both of them were of n by 2, so both of them were like a balanced call, like this. Every time they were getting balanced, right? If one ends over here, the other also ends over here. It was a balanced recursive call structure. But in this example, what happens is, what may happen is, one part may grow like this. I mean, recursive chain may grow like this, and let's say the other would end just over here, the smaller part. So I would always have to consider the more number of recursive calls because I need to consider the worst case time complexity. So I consider the part of the array which actually runs for more number of recursive calls, which is the larger part. That's why I take the complexity of the larger one, because I consider the worst case time complexity. Now, what is the worst case time complexity? Obviously, you know, you are breaking the array every time into n by 3, n by 3, whatever, that way. So I'm writing it as n log of base 3 by 2n. Now again, if I just write something like this, order of n log of, let's say, base 2n divided by log of base 2 3 by 2. Again, if I write this order of n log n base 2, this is a constant, correct? This is a constant. We know that in asymptotic time complexity, we do not consider constant. Fine, so just ignore it. So what do we get at the end of the day? It's order of n log n base 2, which was simply like this for n by 2. Fine. So when we are considering asymptotic complexity, the base doesn't matter. Okay. So whatever be the whatever be the division of the array, whether it is 2n by 3, n by 5, 4n by 5, 1 by 2, 1 by 2, whatever be the division, unless and until it is n by 1 and 1, that is, the pivot is placed at the extreme, either the first or the last extreme, right? Other than that case, in any possible division of the array, it would always be n log n. The reason for that is the base is changing depending upon the size of the division, the base of the log. But that doesn't matter in asymptotic time complexity, because always we can do this thing. right? We can simply, by the property of logarithm, we can do this. Fine. So when it is asked whether what is the asymptotic time complexity of quicksort, when the quicksort divides the array into two parts of length, say A1, A2 and B1, B2. In both of them, it would always be n log n, unless and until A1 is equal to n minus 1 and A2 is equal to 1. That is only in this case, it would be order of n square. So this is very important. Keep this thing in mind from interview perspective, from exam perspective, everything. Is there any doubt in the reasoning? You want to ask something, you want to tell anything? Any doubt? Why this is always n log n? Other than n minus 1 and 1 case. In this case, it would be n square. Other than this case, every time it would be n log n. Fine. Anyone has doubt? Okay. So that's done. Now, one important point again, I would like to just share, and then we would actually do, I mean, we would be completed with the sorting part. See, quicksort is also memory friendly. Now, what do I mean when I say memory friendly? So it is actually very easy for the hardware to do quicksort rather than merge sort. Now, why I am saying so? There is a concept called locality of reference in computers. That means when you actually refer to a value stored in the memory, there is a greater, it becomes easy for the computer if you, again, the next reference to the next data item is located at a memory which is near to the data item that you referenced earlier, right? Any memory, I mean, any data reference which is there in the memory, if that is located at a place, located in the memory where just beside where the data that you referenced earlier to this is there, then it becomes very easy for the computer, for the system to refer to that value. If I draw it over here, what I mean is, let's say this is your memory. What memory, what is RAM and all those things, I'm not going. Just suppose this is memory. In this memory, one value is over here, other value is over here. So let's say this is contiguous, huh? Let's say this is the continuously stored memory. I mean, this is the first part, then this is just beside it. So if your algorithm refers this value and then it refers this value, it becomes easy for the program to, it becomes easy for the system to do the work. But in the memory, if your values are distributed, I mean, far away, let's say A is over here and B is over here, right? You reference A at first and then you reference B, and there is a gap in between, right? Then it becomes somewhat difficult for the hardware to work, right? So asymptotically, everything would be same, complexity would be same, but at the end of the day, you would actually run the hardware, right? So the hardware performance would give you a better result on this kind of algorithm, which refers to value which are nearly located. Now, I'm just mentioning this. Those of you who don't understand, it's okay. But if you're interested in this, you can also further read and ask on discourse. We would go into, I mean, I would try to explain in detail over there also. I would not go into detail in this session about that. So this is called locality of reference. Fine. That is, whatever value you are referencing, what is the locality in which it is present. So merge sort, if you just think about merge sort, what it does, let's say, what were you doing in merge sort? You have one array, right? Let's say this is the division, and this part is sorted, and again this part is also sorted. Fine. And you are comparing these element with this element and find which one is smaller. And the one which is smaller, you used to put that into a separate temporary memory location over here, right? Whichever one is smaller, you put it over there. This is what you used to do in merge sort. Now see, this value in the array is located over here, right? Let me use another color. It is located over here. But this value with which you are comparing this one, right, is located over here. There is a memory gap between these two. Fine. These are not contiguous. Correct. So that's why merge sort compares elements which may be located far away in the memory, and that's why it is a little bit, from the memory perspective, it's not that good corresponding to quick sort from the hardware perspective. But in quick sort, what happens is the partition algorithm, right? This is what? This is the merge algorithm. This is the partition algorithm. What will happen in the partition algorithm? Let's say I consider this as my pivot element. Fine. From where will I start? I will compare this element with the pivot. Then I would compare this element. I'm proceeding in a sequential manner, right? And let's say if I take the first element as pivot also, in that case also, let me delete it, sorry. That is, it is a sequential processing. You always do compare elements which are located one after the other. If you consider this as the pivot, right? This is your pivot. In that case also, how will you proceed? Just the next element you would compare, right? Again, you would compare the next element with pivot. Again, you would compare the, so you are proceeding like this one by one, just adjacently. Here you had this gap. You are comparing this one with that one. Then let's say whatever, let's say this element moves in over here. So you are again comparing this element with the next element which is over here. So again, there is a memory gap of this much. Getting the idea? So this is what we call locality of reference. So merge sort is not that good in terms of locality of reference, but quick sort is again very much better in terms of locality of reference. So this actually allows quick sort to work better on the hardware rather than merge sort. But again, there is again one condition coming into the play, that if the data set is very large, then the hardware optimization may be overcome, maybe overshadowed by the extra time that quick sort may take when you have order of n square cases coming. Right. So very interesting, right? You can have the algorithmic point, that is the timing point, and also you can have the hardware point. There are both ways, both advantage and disadvantage. You have to figure out what I should choose depending upon the use case. Right. So quick sort is good for lesser amount of data. And again, when you are kind of sure about the locality, merge sort is good when you have a huge set of data because you don't want to take any risk. But for small amount of data, quick sort is recommended because of these small reasons, that you do not need extra space. You do not need the recursive stack that much. Recursion is going on, but not as much as merge sort, right? Thirdly, the hardware is more friendly with quick sort because the locality of reference is there. Fine. I just mentioned this point. If you have interest, you can post it on Discord. We would give more detail about it. Any doubt? Any one of you want to ask anything on it, or we would move to the list and array difference, those points?
Can you hear me?
Yeah.
Yeah, so in the question also in the graded assignment 2, they were asked for efficient. They have mentioned only efficient, so I don't know whether to choose. I know, for example, the sum is like a student is added inside a list. So I chose as thinking of time complexity, I chose as merge, but actually it was wrong. It was, the answer is insertion sort. So the word efficient, I thought it's time complexity. So how can we choose in such a cases, whether to think of time complexity or anything else?
No, sorry, I could not actually get. Can you tell again what was the question asking you?
Yeah, the question was, when a student list, a new student is added, sort is best. We have to choose efficient method. That's what the question was. It's a graded assignment in 7th question last week.
Yeah.
So
okay.
I initially thought as insertion will be best, but because it is mentioned as efficient, I was thinking on the basis of time complexity and chose merge sort, but it was wrong. So in that scenario, it is tough to choose which one is the best.
Yeah, see, that's the thing. So when it is already told you that there is a list there and you have to just put one element, right? I mean, one value, right?
Yeah.
One student.
New student. Yeah.
Yeah, you have to put one value. So when you are doing that, that's the reason, right? I'm telling you that one value, when you have a large set of values, it's better to go for merge sort, right? And when you just have to need put one element, what happens if you do merge sort? In order to put that one element, merge sort would break it down at the bottom level, and then it would again combine the whole thing. That is not required, right? Insert sort would do it in order of n time.
Okay.
So these things, these comparisons would come into play. It's very difficult, I mean, to judge it. And
so, but definitely we should not go for time complexity, right? In every case, you should not think of time complexity.
In every case, you should not. Time complexity comes into action when you are generalizing the algorithm in terms of the input, right? So what is time complexity? When you have a huge data set, what will happen? That's
okay.
Correct. So when the problem is already telling you that you do not have to work on a huge data set, just one student would be added.
Okay.
Right? In that case, you don't need to consider time complexity.
Okay, thanks a lot.
Yeah. So read the problem statement. If the problem statement or question is telling you that one specific instance, that this is the current state of my data structure, this is what I want to do, and this is the only thing that I want to do. I'm not asking you in general. I just want to do this operation. Then you have to consider that what is the current possible scenario. You should not go by time complexity only, because time complexity would help you when I'm asking you in general that for a large data what might happen. Got the idea?
Yeah, thanks.
Okay. Yeah, someone's mic is unmuted. Can you please mute your mic? So voice coming. Okay, so that was for quick shot, best case, worst case, merge sort comparison. These things I have done. So in general, any doubt in quick shot? Otherwise, we'll move to the list and array.
We will practice and come back.
Sir, I have a doubt, but I'm putting it on discourse. It's about locality of reference.
Sure.
Yeah,
I don't want to discuss it in the session in detail, because that is not there. On discourse, we would answer. Fine. Yeah. Okay. So now let's move to the analysis of quick shot is also done.
Just a quick query. In PDSA, we are not getting. I mean, graded assignment solutions will not be provided. That is what I understand. Correct?
Assignment solutions, the live coding ones or the normal programming assignment?
Graded assignment. Graded assignment.
No. Yeah.
Yes. Then when after the assignment deadline is over and we are receiving the feedback in the assignment section, many times those feedbacks are even convoluted, difficult to understand.
Okay.
So will it be like we will be discussing each and every graded assignment question in one of the live sessions? Because many people might have doubt on different questions.
Okay, fine. So let me just ask all of you to do this one thing. On discourse, we would start a thread. I would start it by tonight. All of you who want that to be done, to discuss the graded assignment solutions, right? Comment that and we would think about it. Fine?
Sure. Why? Because just to, for example, there is this question number 10 in week 2 graded assignment.
Yeah.
And the feedback given is just a one-liner. And
I understand. Programming.
Yes,
Yeah. Okay. Surely. Just write this thing on the discourse, and we would think of something like that. Surely. Maybe on an on-demand session on every week. Maybe we would do something like that. Okay.
But those, yeah, I mean those threads are yet to be started. Correct?
Yeah. I have not started. I'm just telling you now because you said. So I would start it by tonight. Maybe you all can comment by tomorrow. Right?
Thank you.
Sure. Okay. So average case, best case, all these things we have discussed. Randomization of quick shot is also discussed. Iterative version of quick shot. Quick shot in practice. Fine. Order of n square thing is done. concluding remarks on quick sort is I mentioned all these points. Row stable stability. Okay, stability is one important point. See, what stability means is, let me just, what do we mean by a stable sorting algorithm? So let's say I have a collection of data in which I have repeated values, say 6 and 6. And with each of these, you all have learned about objects in Python, right? So let's say I have an object. So this is an object, right? This whole thing is one object. So this is like a list of objects. And let's say I have the corresponding character over here. Let's say I have A, B, C, D. Fine. All of these are objects. So we have a list of objects. Now I want to sort this list on the basis of only the first value. So let's say this is the first value, this is the second value. I want to sort this list of objects only on the basis of the first value. Fine. So we have this repeated value. This is 9. Huh? Yeah. So we have these two repeated values, right? Two repeated objects, 6b and 6d, which have the first value as 6 in both cases. So stability of an sorting algorithm means, what if I would call an algorithm I would call a sorting algorithm as stable when after the sorting happens, the 6 corresponding to B, which is earlier, right? This 6 which is corresponding to B is earlier than the 6 which is corresponding to D. Although the value of 6 is same in both the case, and I am sorting only on the basis of the first value, still after my sorting, the 6 corresponding to the B value, which was earlier, would remain earlier in the sorted sequence. Fine. So my sorting order would be something like 1F and followed by 2A, followed by 4C, followed by 6B and not 6D. Then it would 6D and then finally 9D. I will not place 6D before 6B because in the initial array 6B was before 6D. Fine, this is not allowed. So if I get this result in every iteration of the sorting, sorry, not every iteration, on every run of the sorting algorithm, then I would say that that particular sorting algorithm is stable. But if in some sorting algorithm the result is correct on the basis of the first value I am sorting, so the result is correct, but let's say B comes over here and B comes over here, that is the object corresponding to B moves after the object corresponding to D. In that scenario, I would say it's not stable. Oh, that is stability. Now quicksort is an algorithm which is not stable. One important point, this does not mean that anytime you would not get the stable result, right? Non-stable algorithms may give you stable result, but that is not a proof. Proof means you have to always give stable result. Fine. So merge sort is an example of stable algorithm. So it would always give you the stable result. Quicksort is not. Quicksort may actually interchange the values. So that is what we call stability property of sorting. You got that? Any doubt?
Sir,
Why merge sort will always give stable?
Sorry, can you repeat? Why quicksort is stable? Sorry, merge sort is stable.
Yes,
Why
sir.
merge sort will always be stable?
Why quicksort is not, may not be always stable, right?
No, merge sort, sir. Merge sort. Why is merge sort?
Anyways, yeah, merge sort is stable. The reason for that is, see, when you are doing merge sort, how are you actually working in merge sort? So let's say,
Can we use the same example which you have used here, sir?
only fine. Okay, wait. When I'm breaking in merge sort, right? when I'm doing the break in merge sort, every time it is done on the, I'm just showing you the breaking tree. So let's say 2A, 6B, 4C, 6D, this is the right. So I would break this 3 element into the first. So 2A, 6B, 4C would be the first set, 6D, 9E, and 1F would be the second set. Fine. What would be the next break? The next
Got
break
it,
would
sir.
be, got it. I even did not go up to the root level. Anyways, see, you can see the pattern over here. Merge sort is not interchanging the values. It's always breaking. If 2 is on the left hand side, okay, so leaf node I don't want to say now. I mean, at the last level of breaking, when you break it down to single element, right? You are not interchanging 2 with something else on the right hand side. Okay, so let me just again do the iteration. So 2A, 6B would be the second break, and over here let's say D, 6D and 9E would be the second break along with 1F. Fine. What would be the third break? Now it would be broken totally 2A, 6B, 4C. Over here it would be 6D. This is the line. Sorry, this should not be the line. This is the line over here. This is the line. This is the line. This is the line over here. These are the lines. So 6D, then you have 9E, then you have 1F. Correct? This is the breaking. See, I have not disturbed any order. What we are doing is we are simply dividing. Now see what happens. Now I would do the merging, right? The merge algorithm. This is the recursion call. Remember, whenever we learn the merge algorithm, we do merge sort. We do the merge sort 2 times, from beginning to mid and mid to end, and after that we consider that both of these recursive calls sorts the 2 subparts of the array, and then in the merge algorithm we merge both the subparts. So now this is the decomposition phase. Now we would do the conquer phase of the algorithm, that is the merging phase. So now merge is coming. So from here merge works. Now see what happens. I would, let's say 2A and 6B I would do. So 2A, 6B is merged. 4C remains 4C over here. 6B and 9E is merged. 1F remains over here. Fine. Now I merge these things. So 2A, 4C, 6B. And here it is 1F, 6D, 9E. Fine. Now again I would do the joining, right? Merge. So can you see the thing that I'm not interchanging value? In partition algorithm, what will happen is I would pick one element pivot randomly and then I would place it at its proper place. And in order to do that, I would swap the elements from here to there and there to here. Right? So this can disturb your order. But in merge sort, it's not disturbed.
What if 6D was written in place of 6B and 6B was written in place of 6D? Like in the upper example, if we just replace the B and D, how does this work, sir?
Sorry, I did not. If the initial array, if the initial array of objects had 6D in front, then merge would keep 6D in front in the sorted sequence as well. That's what stability means, right?
Yes, sir. So it would be 2A, 6D, 4C, 6B,
correct,
9E.
Exactly. The point of observation in this is that you are not exchanging or swapping values from the left subpart to the right subpart. Got the point? What I'm saying? Am I changing anything? Am I bringing from anything here to here and there to here? No, right? Am I changing anything from here to here? No. Everything.
No, I think the confusion was because this ABCDE in the sorted order which was there in the original array.
Yes, I assumed that
Anything. I mean, A, I,
Okay, got it.
anything random from the
Any random, sorry.
then that should be preserved.
Yeah. Just a second. Don't think it like that. It's not. It has nothing to do with the sorting. Is not done on the second one. Let's say G I K L M N. Fine. In that case, 6. The sorted order would be 1N, 2G, 4K, 6I. Why 6I? Because I is the 6I was before. Then you proceed the way it is. 6L, 9M. Fine. It has nothing to do with the sortedness of the second one or the third one. So this is called stability. Okay. I mean, whichever is there in the initial state of the array, right? That whole thing would be there. Even, I mean, for repeated values corresponding to which you are doing the sorting, right? The other, I mean, that corresponding object which is there initially at the initially in the array, in the sorted sequence as well, that would come at first. Fine. So 6I would come at first before 6L in merge or in any algorithm which is stable.
Sir, why is stability important then?
Why stability is important? Okay. Now, that is something which is in application specific point of view. We can tell you that. See, let's say you are designing a system, right? In which okay, in real life. So in real life, this is highly used in computer networks, but I'm not going into that definition. Let's say you are designing a system where there are multiple users who may be mapped to a particular value or an ID, so to say. Now, these users will have details, right? They have their own details. Let's say name, whatever. I mean, some details. And these IDs are unique, not unique. These IDs are something that is generated randomly, and each user is mapped to a particular ID. Now, the thing is, let's say 2 users get mapped to the same ID. That is also possible. Let's say these IDs are lab numbers. All these users are student, and these IDs are lab. It can always happen that a particular lab may be allocated to more than one student. Correct. So these students who has their own details apply to get a particular lab, right? And they are mapped to a ID corresponding to that lab. Now the lab number 6 in our example, that 6 ID, 2 students whose name is I and L, right? They actually apply for it, apply for the lab. Okay. Now after I have the whole data set, I can see since 6I is in front, so within the 6 lab, I has applied first before L. Got it? Within the 6 lab, I has applied before L in the unsorted area. Sorry, in the request, or maybe say you just clicked on the lab number, right? And then you get allocated that lab. So I has done that first, and he got 6 lab at first. So that's done. My data collection is done. Now, as a teacher, I want to sort the whole set of data in the order of lab, right? First lab, second lab, third lab, just like that. So in that case, I must keep in mind all of the students who were allocated to a single lab, the order in which they actually got allocated inside the single lab, that should remain same, because that is the priority, right? A single student, he got the chance first, so he should be in that lab first. Got the idea? So that's where you need stability. When you need to preserve the detail of the time instance,
Order in which they came in.
Fine.
I understood with the network reference, sir.
Yeah, I'm not giving you the network reference again. If you want, put it on, just give a idea on Discord. We would reply in detail how it is used in networks. Huh? So basically,
kind of particular queue should be maintained.
Yeah, exactly. A queue is maintained, and it is somehow used in a customized version of TCP connection. TCP acknowledgement. So in app dev, you all must learn TCP connections and all. So there is okay. Anyway, so in TCP connection, there is, in a customized way, there is sequence number checking, and that is done using this method. So okay, so yeah, we would give this in detail if someone asks on this course. Fine. So that is done. You got the idea, right?
Yes, sir.
Okay. So that was stability. These things are done. Stable sorting is done. Best sorting algorithm, I think we discussed the first 1 hour regarding that although quick sort is n square, but when you have less amount of data, you can always consider that, because that for less amount of data, n square would also be less, and quick sort gives you a much more better hardware optimized algorithm because of the temporal locality. And I discussed that briefly, just the basic concept, right? And also secondly, quick sort also helps you because the bookkeeping work, which sir has also taught all of us, right? That bookkeeping work is less. Now, what is that bookkeeping work? Just understand that bookkeeping requires some extra space, right? In order to do more recursion or unnecessary recursion for small amount of data, you need to put the data corresponding to that recursion into a extra space, and that is actually a step, which is we call the system step. So that is more in merge sort, which you require more in merge sort. In quick sort it is also recursive, but it is fairly less corresponding to merge. Got the idea? So that is the bookkeeping work that goes on. So you need extra space, you get less hardware optimization, but at the same time, for larger amount of data, you get an overall n log n time. So that is good for merge sort. But in quick sort, it is always good if you do that for small amount of data. Quick sort is more favorable. Fine. Heap sort is there. We would discuss heap sort in subsequent weeks. What is heap and all. So yeah. Okay, so list and arrays, I would briefly discuss one important point, the basic thing in list and array, and then discuss one point which was also asked on discourse. And then, yeah, so this. Implementation of list and okay, so what happens in Python is, what is a list? Internally a list works like this. So let's say you have a list, you have value 1 4 7 8. So this is your memory, huh? Let's say this is your memory. Okay, and let's say the memory address is over here, let's say 0x. So memory address typically starts with 0x. It's not important, I'm just writing it in that manner. And let's say 100 or 1001. Fine, this is, let's say 0x 1002 dot dot dot. Let's say here we have 0x7002 dot dot dot, like that. Now what will happen is 1478 is there in the list, right? So let's say 1 is stored over here, 4 is stored over here. One important point is I'm considering each of these values storing a single byte of data, which is not really the case, but for ease of understanding, I'm considering single byte of data, and that's why my 1 is stored in 1001, 4 is stored in 1002. But if let's say it takes 2 bytes of data, then 1 would be stored in both 1001 and 1002, because each of this address corresponds to a single byte of data. But don't go into so much complexity, just understand 1 is stored at 0x1001, 4 is stored in 0x1002, and let's say 7 is stored over here and 8 is stored over here, right? Now you as a programmer see the list like this, but how the system interprets this list internally is, how Python does that is, here it would store up the reference to the address 0x1001. Here it would store a reference to the corresponding address where 4 is there. That is over here, right? Accordingly, this also goes over there, this also goes. So this is going over here, 7, and this will go over here. So basically, internally to the system, a list actually stores the memory address in this format. So this cell would actually store the value 0x1001. So whenever you write L of 0, right, what Python would do is it would go into the first cell, it would see what is the memory reference, and it would go into this memory reference at 1001 and fetch the value which is stored over here and give it to you. Okay, please understand that the list is not directly storing 1, 4, 7 and 8. It is storing the memory reference internally where those values are present. And one very important observation is these are discontinuous. See, 1, 4 may be, these two values are continuous, but all other values are discontinuous in a list. Got it?
Sir, 8 be stored in a prior memory location and 1 be stored in a much later memory location?
Sorry, I could not get. Can you please repeat?
Since this is just referential, I understand lists, I understand array.
Okay.
I wanted to know if in lists, 8 can be stored in 1001 and 1 can be stored in 9021.
Okay. Then?
Like, can it happen like this, or is it always sequential? Like
it can happen. It can happen.
Okay.
Right? This is just random, so it can happen, and it is actually one of the advantage, and because of that, you can create list of large sizes. So that is some observation. Okay, let me just come to that later. I would circle around this point again. Huh? Just give me some time. So it can happen for the brief answer. So one important point is you see in list 1478 is there. You as a programmer see it as a continuous data, but in real life in the memory it is not a continuous data. It is located at maybe discontinuous parts of the memory. What is continuous is these memory references, that is the value of the memory where this 1478 is there, that is stored in the internal to the system in the list. Like this value, this cell would store 0x1001. This cell would store 0x for 4, right? 4 is 1002. Like that. So this is your list. Now what is array? Right? In the NumPy array that sir has taught us, I am not going into the whole detail of the lecture. You should see that and then again visit this live session if required on the YouTube. In the NumPy array, what is the difference is it's not discontinuous. It will be continuous, and also there is no question of these reference things happening. It is just a direct chunk of memory. So what you do is in a NumPy array, you have memory like this, just the same thing. Let's say the array's first element is over here, which is 1, and let's say it's 101. The next element would be over here 4. The next element would be here 7. The next element would be here 8. So considering all of them are 1 byte long, so 102, 103, 104. Fine. So this is a contiguous memory location for NumPy array. Now you can ask, this is the question that was also asked on discourse, and sir has also described that between the comparison of array and the list. I'm just mentioning that because yeah, it's important. See, NumPy array is contiguous in memory, so intuitively it should mean that when you are working on a NumPy array, it would always be faster, because in a list there were references which were pointed to discontinuous locations in the memory. So when you work with list, you will have to go through the you will have to refer to this go to these discontinuous locations in the memory and then fetch the data from there and give to the programmer, right? But in but in array, NumPy array, it's not the case. It's just directly located one after the other. You can just fetch it one after the other. Okay, but if you actually see, as sir has displayed in the lecture, that NumPy array may take some more time when you use a specific kind of operation. What is that specific kind? If you simply iterate through the array using a for loop or while loop, that is, you simply loop through the array and you write statements like, let's say AR represents the array, right? You do this indexing, ARI equal to some work, not equal to any work with AI AJ. That is basically You are running through the array in a loop and then working with the array AI, AJ, whatever. That is, you are doing indexing. Now, why it is that the case? I mean, intuitively, indexing should actually be better in arrays because it's directly located one after the other. See, the reason for that is, so if you basically do a linear search on a list and linear search on an array, you would NumPy array, you would see the list performs better. After a certain, I mean, for as the more you grow the data, the list performs better than a NumPy array. Linear search, linear search using a for loop, you run a for loop and then do indexing to do the comparisons. So whenever you do indexing, that is, you write something like this, NumPy arrays perform that. The reason for that is NumPy arrays are created to do most works in the data science domain or machine learning domain, where you work with a lot of vector operation. Now, what is a vector operation? Vector operation means you have a set of data, maybe an array, I mean, basically collection of data, and you do some operation, some function on this whole collection as a whole. That is, let's say add 2. So you add 2 with all the elements. Dot, dot, dot. It's not that you swap this with this element, you compare this element and this element, right? Not this kind of operation, right? NumPy arrays were created to cater to a specific requirement of machine, that sir has also mentioned that in the slide, to cater to specific requirement in the domain of machine learning operations or mathematical operations, right? Where you actually have to do a lot of vector instruction. Vector instruction, this is a vector actually. When you have a set of data, you can just assume it as an array. You can kind of tell that an array is just a vector. Fine. When you have this set of data, right? So you have to apply a particular function or operation on each and every element inside that array. Then that is a vector operation, right? You are not comparing one with other, swapping one with other. That's not the way. That's not the work that was kept in mind while designing the NumPy arrays. Okay. So whenever you do indexing, you run into problem because the way NumPy arrays are created is these single elements in the array, right? They are not given unique identity. So when you create a list, like in this example we saw, when you create a list, each of this element is just like an object, right? Each of them has unique identity. You get each, you can refer to L1 or L0, whatever. And this value 4 in case of L1 would be fetched because 4 itself is an object and stored in the memory, right? As a part of the list. But over here in an array, 4, 1, 7, 8, none of them has unique identity. They are stored as a vector, as a contiguous chunk of indivisible data set in the memory. So when you do an aggregate operation like this, a function applied to all the element, they are much faster than list, right? In a list, you want to apply a function on all the element. An array, you want to apply function on all the element. Array would be much faster because that's the thing that was kept in mind for making this array. But when you want to do indexing and fetch each element one by one by running a loop, right? For I in whatever the name array, right? Sorry, not a range. I'm doing this thing, so it should be in range of length A. Right? When you do this, then what the system has to do is it first will go to AI, which is in this case 1478. It would copy this, it would create a separate object, create a new object, create new object of int type. In that new object of int type, it would copy the value of 1 and then it would return the reference of that new object to you in case of array, because 1478 has no individual object identity. Getting the point? So that's why when you are using NumPy, aggregate operations or vector operation, which in simple terms, which means when you want to operate on all the elements of the array, right? So those operations are better, but as soon as you come into indexing, you run into trouble. Okay. that is the basic idea. There is a multi-threading point of view to it. I'm not going into that. But yeah, this was the reason for indexing error. So sorry, not error, the mode time in indexing. So when you do indexing, you have to create an object apparently. I mean, not you, the system, the Python system would create an object corresponding to that value which is there in the array, copy that value and then return the reference to you. Whereas in list, it directly is an object, each element, so it would directly return that. So that's why list performs good while you do work of indexing, and arrays perform good when you do operations on the whole data of the array. That is called the vector operation. So those of you are interested, you can search what are vector operations and all those things. Since anyway you are going to learn in machine learning these things, so it might be important. So that was the comparison between and the basic structure of array and list. Yeah.
Sir, one question, sir.
Yeah.
Sir, though the NumPy array is little slow, but all those operations which are done in list, all those operations can be done in NumPy array also, sir?
Yeah, you can do that, no issues. It would take some more time. That's it. And I would like to just again restate that NumPy arrays are not slow. It's just that you are trying to do some work with something that it was not supposed to do. Getting the point? NumPy array was only created in order to cater to vector operations. That is when you are doing some operation on the whole set of data, not comparing each data in that array with the other. I mean, each data with the other one. Right? That is not what NumPy arrays were created for. NumPy arrays were created keeping in mind that you would do vector operation. Vector operation means you do some same function, right? Some same operation, same function on all the data elements present in that array. Right? So if you do something like that, like I said, let's say you want to do add +2 with all the elements in the array. Take a list, add +2 with all the elements, take an array, add +2 with all the elements. That is the idea. You would see better performance. So let's say if I want to do this kind of operation, you have A and B two lists. You want to do, let's say 1, 2, 3, 4 and 4, 3, 2, 1. I want to do this pairwise summing. Okay, for both the list. Right? So you can run a loop and do this summing one by one. Or if you have a NumPy array, what you can write is A plus B directly. Right? If you do it in the form of NumPy array, and you can A plus B. You would see if you run a loop and do this 1 plus 4, 2 plus 3, 3 plus 2, 4 plus 1, right? You would see the time taken by this would be much more. And the time taken by this A plus B operation would be much less. Why? Because here you are operating on each and every element stored in the A array and the B array. So this addition operation is just a vector operation. That is, you are doing something on all the elements. All elements of A gets added with all elements of B, one by one, I mean. Yeah. But when you are doing swapping, when you are doing sorting, when you are doing searching, that is essentially you are comparing one element with the other. It's not something you are applying a function on all the elements. Right? In that kind of scenario, that is when you have to do indexing. Lists are better. Okay.
Sir, can I ask something? If it is beyond the scope, let me know. My understanding of array was since it is on fixed memory location, to reach the I location in an array, it is order of 1 because I just have right. And in a list, if I reach to the ith location, it will be order of n because I have to reach I have to go through each and every element to find out where the next element is stored. So,
exactly.
So in your addition of two arrays, which you just showed
just
us.
One thing, I want to correct one. Yeah, I got it. Just one correct thing. One thing I want to clarify. You said list, you have to travel through all the blocks one by one, right? In order to reach at a specific position. In array, you can do direct access, correct?
Correct.
Yeah. But is Python list the same thing as linked list? What you are saying is essentially linked list, right?
Yes.
When you have one element one after the other pointed by pointers. But I just told you this is Python list. This is not linked list, right? This is just like an array. That's why in the lecture also Sir has mentioned Python list is more like array. Why Sir has mentioned that? The reason for that is you can see the Python list in this form 1478. Internally, Python list is just an array of the memory references. So this is a memory reference. It stores 1001. So that's what I told. This is the array corresponding to 1478. It would store 1001. 4 is stored at 1002. That's it. So now there is no node, there is nothing like you have to travel one node after the other and reach at a specific point. This is just a direct memory reference. You go to that memory. That's it. Fine. So Python list is implemented in this manner, and Python list is not the the traditional linked list. In linked list, you are correct. It would take order of n time, but Python list is not that. Okay. Yeah. Only difference between Python list. Yeah. Please say.
Sir, is list anywhere related to pointers? Like we store the address of a memory location.
Sorry, I did not get. Can you please repeat?
Sir, like in C, we have in language C, we have pointers. Is a list similar to that, sir? Because in pointer also we store the address of memory location.
In pointer also, pointer is nothing but a memory location value, right? You store the value of the memory location. That's it.
Yes. So list is also same, no, sir? Because here also we are like storing the memory location address, and we are fetching the data.
Sorry, I did not get you. I'm not. Can you please say it again?
Sir, in list also we are.
Yeah.
In list also we are storing the memory location address, and we are fetching the data from the memory. Similarly, in pointer also we are doing the same thing.
Pointer. See, do you mean array when you say pointer?
Not array, sir. In C language, pointer.
In C, that is the implementation, right? That is implementation. So I'm not going into implementation over here, right? That's not important in this course, but yeah, it's pointer only. It's just like a pointer which is internally storing the memory reference to that particular location, right? And you are just going to that location, fetching the value and showing it. That's it. Only difference is that in case of list, it has a particular identity. It's just like an object. So you can pick one of them. But in case of array, it's not like that. Now the reason for that is again there is something with bit padding, but okay, again that's something not required over here. So basically you would have padding over here. That's why list can store heterogeneous types of data, but array cannot. A NumPy array cannot store heterogeneous type of data. A list can store heterogeneous type of data. So this memory location, now I just for sake of easiness I took 1001, 1002. But it would not be 1001, 1002. There is a padding. I mean, there would be some extra space kept reserved for each of the elements stored in the list, because maybe in the next element you need more amount of data because the next type is different. Okay, so this padding and other issues are also there in case of list, but in case of array that is not the case, and that's why list has individual identity for each element. In array, it's not that case. There is no padding. Everything is there under one chunk of memory contiguously located. So in order to fetch a value within that chunk, basically the system creates a separate object and then it returns the value. But then that's why it takes more time when you do indexing operation with arrays. Okay.
Yes, sir. Got it.
Okay. So that is done. Now, just a second. Okay, I think only 8 people are left. Just a second. Okay, so I just wanted to again ask for one last time. So sorting and this basic understanding of this is done. after that, we have some simple insertion deletion in linked list, right? So anyone has doubt in the any specific part? Again, I'm asking, so you can tell. I will discuss that part because it's quite late now and very few people are there. So you can ask if any one of you have doubt. Otherwise, you can also post it on Discord. We would answer.
No doubt, sir.
No doubts.
So we have to go through the lectures first, then.
Yeah, you all have not gone through quick shot also. How will you have doubt on linked list? So okay, fine. So once you
That's
go
why.
through, okay, go through it and then post it on Discord. This week also we have this celebration and all, right? So most probably we will not have any other live session. And in the next week, if it is required, we would also have one extra session if it is required, and then maybe we can address those things. Fine.
Thank you. Thanks a lot.
Sure.
Sir, whether the events will be telecasted live, sir?
I am not the
Those-
correct guy to ask this. You can ask it in the operational tag in Discourse, right? Or some other authority. I think there would be a telecast. There is a telecast. Live telecast is there, no? There is a telecast. I think you should ask it on Discourse under operational, right?
Okay, sir, because we are not able to go there, sir.
Yeah, I understand. Yeah. There would be a live telecast, but please, you contact the appropriate team. They would tell you. Fine. You can post in Discourse under operational. I hope someone would give you the proper answer. Or you can also tag JK sir.
Okay, sir. Thank you.
Sir, one last question. I didn't understand about the indexing part which you had brought up earlier. I don't know what is in. I've gone through the lectures, but I think I have skipped indexing.
Okay, so I would write an answer on Discourse. Fine.
Sure, sir. Sure.
So this thing and locality thing. Locality thing you were saying you want to post. You post it, I would reply. This thing I would write an article kind of thing and post it. Okay.
Okay. I've posted locality of reference.
Sure.
There was an article about it, but I've also posted mine.
Sure. Okay. Thanks.
Thank you. So late.
Thank you, sir.
Thank you.
Bye-bye.
Bye.